We will study velocity time graph. First of all, velocity is taken along y-axis and time is taken along x-axis. Velocity is taken along y-axis and time is taken along x-axis. Then I can say actually velocity time graph and speed time graph are same if body moves only in one direction. For example, if the body is moving towards right only in this direction, then it doesn't matter whether you call it a velocity time graph or speed time graph. But if the body changes its direction, one question, then it's always the velocity time graph. So what's the gradient? Gradient of the graph. Actually, you can always go for the gradient of the graph. Units along y-axis, it's a meter per second upon second. So it's meter per second square. So meter per second square is the unit of the acceleration. So gradient of the graph is acceleration of the body. So gradient is positive, it's acceleration. If gradient is negative, it will be deceleration. Then area under the graph, is the displacement. Why is the displacement or distance? Because if your area under the graph units along y-axis is meter per second into unit along axis second, so it's just a meter. Meter is the unit of displacement or distance. So area under the graph is the displacement. We take like this one. This is the velocity time graph. Time, velocity here, positive. This is going to be positive. This will be negative velocity here. This is zero. Velocity time graph. If I take speed time graph and velocity time graph, same if the body moves only in one direction, then this will be the velocity time graph or speed time graph. Now let us, I'll first discuss a few important graphs for the velocity time graph. Let us see how we can first actually I will discuss some important velocity time graphs. Some important velocity time graphs. So important velocity. Actually, I tell you that is the velocity time graph which is most important, and your examiners actually test you 90% times in velocity time graphs. So this is a very important lectures. I think I can record more than 2 lectures here for the velocity time graph. I'll be thinking how many lectures I should take for the velocity time graph. Some important velocity time graphs. First is, I can say, suppose if the body is at rest. If the body is at rest, how I can actually, it means the velocity is 0, so I can take displacement time and speed time or velocity time graph is same. So if body is at rest, I will take this portion. So velocity is 0, this one. Then this is the clearly when the time is passing, velocity is 0. So the body is at rest in velocity time graph. But suppose if the body moves with constant velocity, then how I can find? Suppose if the body moves, second is the body moves with constant velocity. If the body moves with constant velocity, then I can have velocity time graph like this one. And suppose the velocity is positive, it is moving only in one direction, this one. So this is, suppose I can say O, A, B, C. This is the graph. The gradient is constant, means velocity acceleration is 0, and body is moving with constant velocity. It has a velocity suppose this is AB, what will be this area? This will be just the displacement or distance. For example, if you have the graph of this one, suppose time in seconds, and it's the V meters per second square, and he says it's 50 and it's operate for 10 seconds. It means body moves with constant. You can always, actually you should be able to translate a graph into words or words into graph. That's always, you must know this. I can translate this graph, body moves with a constant speed of 50 meters per second for 10 seconds and covers a distance of how much? This is the distance area under the graph. How much is the distance? The displacement is 50 into 10. How much is 500 meters? So I can entirely transfer this graph. I will say for this one, body moves the constant or uniform velocity or speed. Here I can say speed of 50 meters per second for 10 seconds and covers a distance of 500 meters. And suppose if I am giving this line, anyway, I should be able to translate it. For example, suppose if you are given like this one, this is the time, this one. They say body moves with a constant velocity for 20 seconds, and they say they cover distance of 1000 meters. What is the constant velocity? So I can say this is constant velocity u, 1000 meters, this in 20 seconds. So the area under the graph is u into 20 will be 1000. So u will be 1000 divided by 20. So it's how much? 50. So u is this again, 50 meters, and it covers 1000 meters in 20 seconds. So in that way you work with the constant velocity. But velocity is not usually constant, and in our course that is the constant acceleration. If it is the constant acceleration, how the graph looks like? Suppose body moves with constant acceleration. These are a few types of the graphs I am discussing. Body moves with constant acceleration. If the body is moving with constant acceleration, the graph must be like this one. This one. This is the constant acceleration because the gradient of the velocity is constant. Now, if suppose I can have the different values for this one. This is the okay. But if the different values are given, how I can find from this graph the different values? Actually, always for each graph you must know the initial velocity, final velocity, acceleration, displacement, time. 5 parameters, 1, 2, 3, 4. If the values are given, you should always be able to calculate these all 5 terms, and then you can express them in words. Or words are given, you should be able to express them in the graph. For example, if it is said, suppose in words, if it is said body starts from 0, starts from rest and moves for 10 seconds and achieves a velocity of suppose 40 meters per second with constant acceleration. First of all, see how I can sketch this graph. I will say the body is moving with and this is the time in seconds, and this is the velocity in meters per second. It starts from 0, 0 with constant acceleration to this one. I'll be giving the values. This value is 10 seconds and this value is 40 meters per second. Now let us see what are its initial velocity here. Its initial velocity here is u is, I can say it's 40 meters per second, and initial velocity is 0. It starts from this 0. Final velocity is 40 meters per second, Acceleration, how I can find the acceleration? Acceleration is actually the gradient of this graph. If acceleration is the gradient of this graph, I can find this acceleration, gradient of this graph, I can find it. See, I just find the acceleration, the gradient of this one. So gradient, you can just take this triangle. This is 40 upon 10. 40 upon 10, so acceleration is 4 meters per second square. And what the displacement? Displacement is area of this triangle. Area of this triangle, and it is 1 upon 2 into base into height 10 into 40. So this is how much? This is 200 meters, and time already is given to you, that's 10 seconds. Anything, suppose if the graph is given, you can always find that thing, if the graph, if the words are there, you should always be able to sketch a graph on that one. For example, if I say a body moves with initial velocity of 20 meter per second, accelerates uniformly with an acceleration of 5 meters per second square for 10 seconds. First, now you have to sketch this graph. So see how I will sketch this graph. So time in seconds is the velocity in meters per second. So now it has a velocity of 20, I can say this is the 20, and a constant acceleration like this one, and this graph is almost how much? This time is 10 seconds, and he has given acceleration. We usually write acceleration along this one, although this is not the length, but this is actually the gradient, but we usually write acceleration along this one. Acceleration is 5 meters per second square. Now let us calculate the different values u, v, a, s and t. This is 0, 0. Of course, t is given 10 seconds. Initial velocity is given 20 meters per second. Now let us see, we are not being given the final velocity. Acceleration is given 5 meters per second square. So first I'll just find what is this velocity v, suppose this one. I can calculate this length, only this one. If this is suppose x, I can calculate this x. Actually this is 5, this is x, and this is clearly 10. So I can say 5 is equal to x upon 10. So x is how much? 50 meter, 50. So this x is 50. If this is 50, this is 20. So the v must be how much? 70. So v comes out to be 70 meters per second. I have not used the equations of motion, but see how I calculated. Since the acceleration is given to you, this one, 5 meter per second square, the acceleration is given to you. And see, then this time is given to you. This is, suppose this distance, this is 10 seconds. So I just calculated this value x. So 5, gradient 5 is equal to this x upon this 10. So x comes out, this is 50. If this is 50, this is 20, so this becomes 70 meter per second. Now let us see what is the area under this graph, because the displacement is, although the graph starts from here, but this should be the displacement. Now you can find this by two ways. Either the area of this rectangle, area of this triangle. If you do in this way, area of this rectangle is how much? This is 20 and it's 10. 20 into 10 plus area of this triangle is 1 upon 2 into this is 10 into this is 50. So this coming out is 200 plus this is 250. So it is 450 meters. Another method, you can calculate the area of this parallel, this trapezium. Area of trapezium is always equal to the trapezium. Area of trapezium is always equal to 1 upon 2 sum of parallel sides into height. So it's 1 upon 2 sum of parallel sides. This is 20 and this is 70. So again 20 plus 70 and height is 10. This is 5 times. This is 90 into 5 is again the same value, 450 meters. So this is another method. Sometimes the questions become actually very much complicated when the things do like this way. This is a very important question. Let's see. Suppose, for example, they say a ball is thrown upward. A ball is thrown upward. Let's take it this way. A ball is dropped. A ball is dropped from a height of. A ball is dropped from a height of 45 meter. A ball is dropped from a height of 45 meter and reaches 45 meter. Okay. Suppose they say calculate the time required by the ball to hit the ground, and they also say calculate the speed by which ball hits the ground. Now first of all, this is the ground. Ball is being dropped from here. Dropping its initial velocity is 0. You can take this situation by using equations of motion, but I want to solve this question by velocity time graph. So this is the actual situation. Use 0 and ball hits it here with some speed velocity v. So let us see how I can have a velocity time graph for this one. If this is a velocity time graph, ball is only hitting, so velocity is only this one. I am taking this velocity as a negative because the ball is coming down. Ball is coming down, so the velocity and it's the time. It is coming down here. The 0 velocity, and it just strikes ground after how. This is 45 meters. Okay, this area is 45 meter, and this velocity is v. Now this t is not given to you, but this acceleration due to gravity I am taking just as minus 10 meters per second square. That's given also. Let's say take g is equal to 10 meter per second square. Now first of all, this is v and this is t. I can say area under the graph is 45 is equal to 1 upon 2 into v into t. But neither v is given, neither t is given. So how this just I have calculated this values. If downward is negative, if you take downward positive, then you can have this graph also. This is the velocity in meters per second, time in seconds. If you take downward as positive, the graph comes like this one. This is the time, and this is the v velocity, and this is 45 meters, and this acceleration then is plus 10 meter per second square. Plus if you take downward positive. In both cases, this is 45 equal 1 upon 2 into v into t. Now I'll first calculate the acceleration a. It is actually, I can say 10 is equal to v upon t, just by the gradient. In both cases, this or this case. So I can say v is equal to 10t. I'll put here v is equal to 10t in this equation. This comes out to be 45 is equal to 1 upon 2 into v is 10t into t. So this is 45 is equal to 5t square. So t square is equal to 9. So t is 3 seconds. When t comes out 3 seconds, I can find this v. So v is now v is 10t. So v is 30 meters per second. So I have all the stuff now. If this situation comes, then see this t is unknown, v is unknown. This is given to you. Then just express v in terms of t, and then calculate area and put in that one. That can also, we can go in that way also. So let us see now another important graphs for these velocity time graphs in practical situation is, suppose when a ball, this example again in a detailed way, suppose a ball is thrown vertically upward. upward from a ground. A ball is thrown vertically upward from a ground. Now, if the ball is thrown vertically upward from a ground, how I can say what should be, how the graph will look like. Let us see how the graph will look like if the ball is thrown vertically upward. Let us see the first actual situation. This is the ground. This ball is thrown from, suppose this origin O. It goes up, it reaches at point A, then it comes here and again reaches at point B, or this one. This is the motion of the ball. Now, if I take upward as positive, how the graph will look like this? If upward is positive and I am here take it downward is positive, both things can be taken. For example, we will take upward as positive. So for this, if upward is positive and this just strikes, so ball is just going upward. Upward is positive. This is the velocity and this is time. I'll write those names where the things are become. Suppose this I am taking the A. This is the B, new names I am giving. This C, suppose A, B, C, not O. O is origin on the graph, this one. Now let us see. If the ball is thrown with speed A, where on the graph, actually this is the speed initial velocity and this must be the point A. And this comes, gradient must be constant, this one. This is the constant gradient. Now this is the constant gradient, this one. Then actually this is actually the point B, where the ball is at rest. This one you can see. From A, ball is coming down, but graph comes down here. Ball is going up, graph comes down. Here is the point. Sometimes students confuse themselves. Actually, this is the graph, and this is the actual situation. Actually, ball is rising up, but its velocity is decreasing and decreasing. So this is the initial velocity and reaches here. This is the A point. This must be the B point actually here. Now, what is the area under this graph? I can say triangle AOAB area is what? It is the maximum height. It is actually the maximum height reached by the ball. It's the maximum height reached by the ball. This one. Then suppose now what happens? Ball is coming down, so velocity is negative. Velocity is negative, so it goes here. This one. So this is. Suppose if this is 0, this is t. This must be 2t. This timing and this timing must be same. Now where is this? This point is C actually, and I can have the better view here. This must be a straight line like this one. This is t, so this must be 2t because time going up and down. And also this area must also be same. So this is C actually, this one. So this A, B, C here, this is A, B, C here on this one. If downward is positive, then how you can take, if downward is positive, this is the velocity in set time. If downward is positive, you start from here. It goes here, this one. This is A point, this is B point, and this is C point. And its gradient is -9. For this one, its gradient is 9.81 meters per second square positive. And for this entire, it's -9.81 meter per second square gradient. Now this A point is B point. If this is T, this must be 2T. This area and this area must be same because this is actually the distance covered, maximum displacement covered by the body. This is when ball is thrown vertically upward from a ground. But suppose if the ball is thrown vertically, suppose I'm discussing here another case, very important case, and this is a very important case. This has come so many times in exam. Suppose if this is the top building, or suppose a cliff or something, it has height h, and ball is thrown from here. This is the A point. It goes here. It reaches at this point B. Then it comes here. This again, this point is C. Then it comes here and hits at point D. This is the actual thing how it's happening. Now how I can represent this in the graph? and let us see how I can find the things. Suppose on the graph I can have a velocity time graph like this one. I am taking here down, upward is positive. First I am taking upward as positive, then I can take downward as positive also. If upward is positive, ball is thrown with velocity u from here. Okay, so if the ball is thrown from A, it means this is the A point. Now it reaches this one. This is the B point. Now what is this? OAB. Area of triangle AOB, area of triangle OAB is nothing but the maximum height reached by the ball from top of the building. If the building are from top of the cliff, this one. Now this ball comes, this acceleration must be minus 9.81 meters per second square. So if these two values are not given, I can find just in terms of this one, and this height can be found, then or height is given, then they can be found. Now this goes here, and the C point comes, suppose if this is time t, this will be 2t time. Okay, and this point is again C, and if this is plus u, then at this point this must be minus u. Okay, I'm just deleting this one so that I can have a clear view. This one, this is the C point. See, A is here, this is A, this is A, and its initial speed is u. This is actually this is the point from where the ball is being thrown up. Now ball goes up, but graph is coming down. That's the point where the students confuse themselves. This is the actual situation, and this is the values of the graph, how the values of the velocity change with time. That's why velocity decreases, and at B it becomes 0. So what is OAB? Area of triangle AOB is equal to maximum height from building or from cliff, building or from top of cliff if it is a cliff. Then it reaches at C, and suppose I am taking this as E point. So what is BEC? Area of triangle BEC is same, again the same maximum height from building or from top of the cliff, and reaches, this is the point D here, this is the point D here, and its velocity will be suppose minus v, and this timing can be suppose the time, any other time, capital T I am taking. It's not related to this T or this T. Okay, now suppose I have to find what is the height of the building. Height of the building is actually, area of this trapezium. This one, area of trapezium, which one? Trapezium ECDT. I suppose this is the T timing, I'm just giving the F. But in that way it is very difficult to find that area. What we do, actually, what is the area of this one? Area of triangle BDF is actually, area of triangle BDF is actually this height BD. It's height BD. So from this triangle BD, if you subtract this one, okay, so I can say what is the height of the cliff. Height of the cliff is very important to note. Suppose height of the cliff will be height of cliff or building, and this is the way how we found it. Actually, we first calculate the area of triangle BDF minus area of the triangle OAB. That's it. Because area of triangle BDF is nothing but the AB, and area of the triangle OAB is nothing but the AB. So if you subtract AB from BD, it comes height of the building. In that way we can calculate the height of the building, and that will the velocity time graphs for this very important situation. Now if you can take, suppose downward as positive, then you can always have another graph for this one or another explanation for this one, but it will be the similar expression which I actually told you, and you may take an opposite way. The signs must be opposite. But for example, if the graph is like this one, this is the velocity, this is the time, this one OA, and this one OB. Now what is this graph? Actually in OA, this is the case of what? Increased acceleration. The case of increased acceleration. Acceleration is constant in OA. Acceleration is constant in AB. But in AB, I can say in section AB, acceleration is greater. Acceleration is greater than in section OA. So I can say this is the increased acceleration actually. So increased, not increasing. This is the increased acceleration. If I say increasing acceleration, that becomes different. Increasing acceleration means acceleration is always increased. It's increased acceleration once it has increased. But if it is a increasing acceleration, then always the acceleration will be increasing, like this one, velocity time graph. This one. This is the increasing acceleration. Means acceleration, the gradient of the graph is always increasing and increasing. But this is the increased acceleration, only once time it has increased, this one. But see, suppose this is the case, so time, this is the velocity time graph, this one, this gradient, and this one. Now this is OA and this AB. In AB there is a less acceleration. There is a decreased acceleration. But it is not the deceleration. Body is again speeding up, but at a later rate. So this is not the deceleration, please. Some students think that is the deceleration. The deceleration should always be like this one. This is the deceleration. Now for example, take another example which is usually comes in exams, and I will solve a few other questions using this one. Suppose what happens about this graph, it's the time and it's the velocity. This is, and this one. This is what happens in OA section. Constant acceleration. AB, constant velocity, and acceleration is 0. And BC, constant deceleration. And area of this graph trapezium will just represent the displacement. In my next lecture, for the velocity time graphs, I'll be just solving a few problems on the velocity time graph, and also I will be proving the equations of motion by these graphical methods also.